Hello and welcome everybody to our presentation of our paper Drop It In Like It's Hot, an analysis of persistent memory as a drop-in replacement for NVMe SSDs. My name is Maximilian and I'm presenting today together with Otto. Furthermore, our co-authors are Lawrence and Tillman. We are from the HBI Data Engineering Systems group and we are glad to present our work here at DaMoN today. Our work is motivated by the fact that many enterprise database deployments today rely on well-known stable databases like Postgres that have been around for a very long time, and these systems put stability and reliability over the adoption of the latest research results, so accelerator adoption or something like that. But the question is, what can we still do to improve the performance for free without requiring any code changes? And the answer that we have in this paper is removing other bottlenecks, and in this paper we want to tackle the disk. So databases like Postgres, if they, for example, run a huge table scan operation, they basically have to wait for the disk to answer the queries. And the idea that we have in this paper is to exchange the disk for persistent memory. Because the good thing is that persistent memory can offer very high bandwidths. We have seen in previous work up to 40 gigabytes per second for sequential reads. While on the other hand, modern NVMe SSDs are physically limited at around 7 gigabytes per second because of PCIe limits, and we interact with persistent memory in general using a standard file system interface, and this enables us to do a drop-in replacement of NVMe SSDs, so we change where all the data is stored and then just can work on the persistent memory DIMM. To introduce persistent memory, we first need to understand what non-volatile memory is. And non-volatile memory is any type of storage medium that retains data without power, so like CD-ROMs or tape drives, anything that doesn't need power to retain the data. And two examples we consider are solid-state drives, SSDs, and persistent memory. To be more concrete, we consider NVMe SSDs. In general, SSDs are secondary storage devices that do not require mechanical components. They are commonly based on NAND flash chips, and NVMe itself is just a protocol for accessing SSDs using the PCI Express standard. From an operating system perspective, SSDs are block devices, so we cannot address a single byte on these drives, and they are inherently parallel, so they can serve multiple requests at once and are not as sensitive to access patterns. On the other hand, persistent memory, or NVRAM or storage class memory, is a memory or storage technology that's more like a SSD between SSDs and DRAM, because it's also persistent, but like DRAM is byte addressable, so we can address each single byte on such a DIMM. And if you wonder, like currently only Intel Optane persistent memory is the only commercially available product. Optane itself is the brand name for 3D X-Point non-volatile memory technology, which is a general storage medium, which is, for example, also used for SSDs. And we shortly note that future PMem storage could largely differ in its observed behavior because it's just may be different on a different storage medium. And to compare PMem and NVMe's from previous work, we see that respect to bandwidth, PMem is about an order of magnitude faster than NVMe's for both sequential and random workloads, and we can see peak performance here again of around 40 gigabytes per second for PMem. And we note that if you want to scale out with NVMe's, you need multiple drives. Usually PCI lanes are not a limitation, but if you want to use more PMem DIMMs, you actually need more CPUs to scale out, and also PMem is more expensive. Right now, it's around an order of magnitude, but pricing of PMem has not stabilized yet. From a systems perspective, PMem again is connected to the integrated memory controllers of the CPU, while NVMe's are connected to the PCI lanes of the socket. Yeah, and in our benchmark setup, we use 6 Optane PMem DIMMs that are interleaved, and we benchmark a single NVMe drive as well as a RAID of 4 NVMe's.
For our microbenchmarks, we try to cover all typical operations that a database management system does in its day-to-day work, which is first a table scan, so essentially a large sequential read workload. Secondly, buffer management. When a database management system wants to process a large amount of data, this data might not fit into the DRAM, so we reading it piecewise into the main memory or writing it piecewise out again. And thirdly, logging, because database management systems tried to avoid rearranging large amounts of data. For example, when we have a huge backlog of write queries or something. Okay. So let's get to the first one, which is table scan. And for this setup, we have every thread sequentially reading a 5 gigabit file. This file is read to a small page-sized DRAM buffer, and this way it doesn't actually touch the DRAM at all, but rather stays in the second level cache all the time. Let's first look at the NVMe, and this is the gray and the yellow lines here in this plot. And we can see that when we are using a 4-drive RAID instead of a single NVMe, that we are needing 16 threads to actually achieve linear scaling over the increased number of drives that we are using. If you look at the persistent memory, which is green here, we can see that we overall measure a lower peak bandwidth than what we have heard before, so below 40 gigabytes. And this is because, well, these numbers that have been trying to get every bandwidth, every last piece of bandwidth out of the persistent memory using manually unrolled, aligned 512-bit vector instructions to move the data when reading sequentially directly from the persistent memory into CPU registers, not even DRAM. On the other hand, our memcopy that we are using as part of a higher level implementation compiles 2 different instructions. We can see that for PMem, we get better performance for more threads and larger page sizes, which is actually in contrast to previous work, but shows us that a highly optimized environment like these benchmarks often build is not always transferable to real-world scenarios like the one we have been trying to build here. We also compare different access methods, in this case Linux I/O and mmap, Linux I/O being open, close, read and write and so on. And we can see for them that Linux I/O, which is the solid line here, almost always has a slight edge over memory mapping the file. Again, we have seen that we compile to different instructions and copy loops in this case. So to sum up the table scan workload, we see that a higher thread count and larger page size is overall preferable. Moving on to buffer management. In this case, we have, again, a 5 gigabit file per thread and also a 5 gigabyte workload. And what workload means depends on the write ratio that is setting we ourselves. So on the left, we have 0% writes, which is essentially now a random read workload. On the middle, we have a small amount of writes sprinkled in, and on the right, a very write-heavy workload. When we are reading into a 1 gigabyte buffer in the DRAM, and this way we avoid caching effects. We are also using 4 kilobyte pages for our workload here. Larger page sizes resolve to essentially the same curves, but they are slightly higher. Let's look at NVMe's again first, and we can see that more writes, so going from the left to the right plots, we see that this increases our bandwidth. And this is because random writes scale much better. We can also see opposed to that NVMe scale very bad in the case of random reads, so on the left. And this is because, well, we have heard before, the NVMe's have a high access latency, and a RAID actually doesn't help with shortening the latency. That stays the same if we have 1 drive or if we have 4 drives. However, the RAID does scale much better when we are writing, on the other hand. Moving to PMem, well, it's quite the opposite because it suffers heavily from more writes. Going to the last workload, which is logging. In this case, we had 3 different setups and 2 different log entry sizes, 128 bytes, so a very small log entry, and 8K, which is also the log entry size that the write-ahead log of Postgres is using. Looking first at Linux versus Linux recycling, the difference between the two is that at Linux recycling, the entire log file that we are writing essentially already has been allocated and has been written to and exists. And in Linux, it's not the case. So we can see that the rate in both cases scales really well because we distributed the log files in a round-robin fashion onto the different drives among the threads. You can also see, especially see, that the speed up of the recycled log files, the recycling, is really significant. And this is also a known effect because the zeroing of new pages in the kernel before writing them into PMem, for example, is known to be an expensive operation. The third setup in our case here is lib-PMem-log, which is part of the PMDK and therefore aware of the storage technology that we are using under the hood. And in this case, it can make use of the different persistence instructions that PMem can do. And we can see that here, especially the 128-byte log entry size gets a huge improvement, or more than 20 times higher bandwidth. And this is because, obviously, we don't need to do an fsync system call every 128 bytes we are writing, but we just need one single cache line write-back instructions, and we are done on PMem. The improvement on 8K pages is also significant, but not as large. And we can see that it kind of crashes in if we are using more threads. And in this case, the write queues are getting overloaded. And this is also an effect that has been observed by previous work. In summary, the log file recycling is critical when doing logging and is also employed already for basically any production-ready workload today. A rate of log files scales much better in multi-thread logging, and switching to a storage-aware library like lib-PMem-log makes a huge difference for small log entry sizes on this new technology.
Let us now continue with an end-to-end workload called TPC-H, which is a benchmark consisting of multiple queries that run on Postgres DBMS. The scale factor we use is 100 gigabytes, and the idea is that we have the same Postgres setup, but Postgres uses different storage backgrounds to store or storage layers to store the data. So we have a Postgres setup on an array of NVMEs, on a single NVMe, and on PMem. We see that in general, all queries are fast or fastest on PMem, the green bars here, but the speed up of PMem varies greatly between the queries. We characterize three types of queries. So there are compute-intensive queries like query 18, where there's no difference basically at all, which are CPU bound. We have queries that are sequential I/O intensive. So for example, table scan operations that just go through the entire table. There we see the effects like here, query 2 or more query 3, that the rate can improve the performance of a single NVMe, and PMem is also faster. And then, most interestingly, we have random I/O intensive queries, which are, for example, index scans, where we fetch data from different locations. And these, for example, are query 5 and query 20, where both NVMe setups are going way out of scale, but persistent memory is pretty quick. And the reason for this is that, as we've seen in the microbenchmarks, random I/O workloads are actually latency bound, and hence the NVMEs cannot scale out using a RAID setup. But on the other hand, the PMem, which is not latency bound, can really play to its strengths here in such a workload. And actually, most queries are random I/O heavy if we use indices, and PMem can really play to its strength here. In general, PMem here is 4.2 times faster than a single NVMe and 3.6 times faster than the RAID. And overall, from the microbenchmarks as well as TPC-H, we get 4 key insights. So first, for read-intensive sequential workloads, a PMem drop-in replacement can speed up the workload significantly without any code changes. So for example, for read-intensive workloads, PMem in our benchmarks outperforms a single NVMe by up to a factor of 11. Second insight is that standard operations do not fully utilize PMem's bandwidth, so actually you should use as many threads as possible and prefer large exercises. This is in conflict with previous work, which suggested specific sweet spots for maximum PMem performance. But again, these benchmarks were highly optimized, and this does not transfer to a real-world scenario. To reach its full potential in the future, Linux and standard library operations should be optimized. A third insight that we have is that a drop-in replacement does not significantly speed up write workloads. But on the other hand, introducing a PMem-aware I/O layer that basically makes use of new instructions in the instruction set that deal with PMem persistence without a system call can significantly increase write performance, because we save the context switches and mode switches into the kernel. And the last insight that we have is that for random I/O workloads, we should prefer PMem over scaling out multiple NVMe's, because random lead workloads are latency bound, and PMem can really play to its strengths here compared to an NVMe RAID. Overall, if you want to achieve highest performance possible and you're not able to do code changes, then it is possible to employ PMem as a storage layer and achieve significant speed up. With the continuing development of PMem and the expected price stabilization, we expect it to become an increasingly also relevant drop-in replacement of NVMe SSDs and as a relevant storage layer. And with that, conclude our talk. Thank you very much for your attention. If you have any questions, we are looking forward to them at the workshop, and also our email addresses are written down here, so feel free to contact us. Thank you very much, and goodbye.